All right, welcome back. This is going to be part 45 of my presentation on the flood and Noah's Ark. And this one here, guys, we're going to start getting into the meat of the Polonium Halos. And so I'm expecting, looking at the slides here, I'm hoping maybe 2 videos and I'll have this done. I'm hoping. And so, but in this one here, we're really going to get into it. And then I'm going to show you some areas that you can go into to further your knowledge. And so this is one here out of all the dating methods that I've been looking into. I think I put more time into this one than any of the other ones, though I am constantly adding to this material. I'm not finished. I don't ever consider myself finished on any of the material that I have. And so, but I want to continually put good information into it to always have an answer for somebody that wants to know it. And so to try to help somebody. But at any rate, if you'll notice on the screen here, this chart here, sometimes you'll hear it referred to as the geologic column or the geologic time scale. And so this is just, you see different types of the way the artistry that they put into it. But if you'll notice all the way over to the right-hand side, you got approximate time boundaries and then life forms originating. And it starts from 10,000 and it goes into millions and hundreds of millions all the way to billions. And so if you go all the way down to the bottom, it says the formation of the earth is 4.5 billion years. And so, again, there was a time when they thought the earth was under 100,000 years. If my mind serves me correctly, I think it might have been around 70,000 years old is what they used to think the earth, that was the age of the earth was. And so it just keeps, again, always changing, always adding more time. I guess they thought 70,000 years wasn't long enough to have all the life forms evolve if given enough time. That's usually the phrase that you'll hear. But now let's talk about granite. Notes on granite. It says there are 3 main categories of rock that make up the crust of the earth. You've got igneous, sedimentary, and metamorphic rock. When you talk about metamorphic rock, it's Greek. It means to change form. Granite is igneous, which is a Latin word, ignis, which means fire. Igneous rocks are formed when hot molten lava cools. Granite rock, also known as basement rock, is found all over the world and makes up most of the continental crust covered by sedimentary rock, the foundation rock of the continents. The process of granite formation has been attempted. They've attempted to try to duplicate the process to make it, but they haven't had any success. So the formation of granite is kind of a mystery to geologists. The oceanic crust is made up primarily of basaltic rock. Since basaltic rock is more dense than the continental granite rocks, the continents rest at a higher elevation than that of the oceans. Now, going on, for the most part, the granite core of the continents is seldom exposed. A glacier flowing over a continent might scrape off all of the sedimentary rock and expose the granite once the ice melts. The granite will then bulge up because of not having any weight on top of it. So sometimes you'll see this. Matter of fact, I'm going to be coming back to this when we start getting into the ice age. But for the most part, you've got the glaciers that will move, and it will create these things called moraines, terminal and lateral moraines. And the front of it, that picture, that's what I'm showing at the front of it there. If you notice the glacier is moving, that's that you see the whole big white area, and then there's like bits of rock and debris that's inside of that. Well, what it does is it ends up pushing the ground, and it causes these areas called terminal moraines. And then what happens is the ice starts melting back and it leaves these areas called terminal moraines. Well, at the bottom of these glaciers is a lot of times you'll see the granite will be scratched. If you look over to the left-hand side, you'll see that. That's what's left behind, and these deep scratches that are made into the granite, and that's what it's talking about. Sometimes you'll see that where the sedimentary layers have been scraped away, and that granite has been exposed. And so, but again, we're going to talk about more about the glaciers and the Ice Age on a later video. But going on, it says, in the late 1800s, scientists began studying rocks with microscopes in order to better understand their crystals and composition. Learning how to cut rocks into thin slices, they turned their microscopes on certain rocks, especially granite, and found small colored concentric circles inside of them. It was eventually realized that these were actually spherical shells that went around a central grain in the center. Something like slicing an onion through the middle and finding circles. That is, circles inside circles. These circles actually slice sections of the spheres were given the name halos. We today call them radiohalos. The technical term is, I'm going to try that's pleochroic halos. That Pleochroic halos. A radiohalo is the mark left around a particle of a radioactive substance by the radiation coming from the particle. It can only form in a solid such as it can only form in a solid such as a rock, since in a liquid or molten rock the mark would dissipate and could not be seen. And so, like this right here, this basically what we're going to be going into is you got this biotite granite. Now, those of us that live in the area that I live in, we're very, very familiar with this. There's a city that's real close to me. It's called Granite Quarry. There's just granite all over the place, guys. And so, and from what I've been told, the area that I live into, if you dig down about 2 to 3 feet, that's all you're going to hit is granite. And so there's just not much on space in between that. About 3 to 4 feet is, like I said, is what I've been told. Though I've had some holes dug in my on my land that appear to be a little bit deeper, but I still want to say I don't think it's any deeper than about 4 feet down. And but excuse me. Any rate, if you'll notice this picture here, that little area that I got in the red box, and then I got that zoomed out, that's biotite mica. Biotite mica is what that is. Now, when they're talking about finding these little radiohalos, if you take one of those little mica areas and put it under a microscope, you kind of slice it real thin, you'll see halos in them, just like this. And supposedly, they're all over the world. Now, going on, there are lots of polonium 218, 214, and 210 halos in granite. It has been found that there are trillions upon trillions of them in granites all over the world. A majority of these polonium 218, 214, and 210 halos have no uranium-238 halos within them, showing they are primary polonium halos and not daughter products. We're going to talk about that in just a minute, which the daughter products decay from the parent isotope. But let's see, they're not daughter products from the uranium-238. Again, we're going to talk about that here in just a second. The primary polonium-218 halos are totally independent of radioactive parents. They are original in all rock in which they are found. There is no evidence that they were caused by uranium in the central grain or by passing uranium streams. Evolution theory says that the Earth was molten for millions of years, but the rock the independent polonium halos are found had to be solid at the time it was first brought into existence, or those halos could not form inside within 3 minutes. The granite had to form in less than 3 minutes for the halos to form properly. Granite then, being a basement rock, forming a thick layer with the continents of the world above it and the basalt and magma below it, all this continental foundation had to be formed in less than 3 minutes. In less than 3 minutes. Now, radioactive atoms are capable of spontaneous changing or decaying to atoms of a different type. A parent radioactive atom decays into a daughter atom in various ways, one of which is by emission of an alpha particle. And I'm going to explain that here in just a minute, but with this chart down here that I've put down here, I've added some stuff to it to help explain. But uranium-238 initiates a chain of steps which ends up in the element lead. Chemical symbol, you got that Pb. The uranium-238 decay chain shown below has some daughters which decay by emitting a beta particle. And that's the ones with the B, which is nearly 2,000 times lighter than the more massive alpha particle. The type of decay is shown by the A or the B. And so now if you'll notice this picture here that I have right below that information, you got 238U, that's the uranium-238. That's the parent that it starts off as. Now it's unstable, so it's going to start to decay. If you guys will remember the carbon-14 that we were talking about, how you have stable and unstable isotopes. That's what we're talking about. And so, at any rate, it starts to decay. So everything that comes after that is considered a daughter element. A daughter element. So it starts to go there. It goes to the right, and then goes down, and then goes to the left, and then goes back down and goes to the right. And then the very last one is that lead. It's the daughter, and it's stable. So it won't change anymore from that. And so, but inside of this chain reaction from uranium-238 to all the way down to the daughter lead-206, there is a long span of time that we're talking about. And what they're saying is that uranium has a long half-life of 4.5 billion years. So it would take that long for all this to happen. And so now inside of this, you've got polonium, the polonium isotopes in there. If you'll notice, it's going to be, if you go down to the second line, you've got polonium right there in the middle, polonium PO218, and then below that, you've got over to the bottom left, you got polonium-214, and then over to the end, right before you get to the lead, you got polonium-210. And so what they're saying is that what they have found in this mica, in this granite, is polonium only. There's no indication where it has decayed from 238. And the polonium has a much shorter half-life span than the uranium. Much, much, much lower. And so, in showing is that the granite that was formed with this polonium, these polonium halos inside of it, formed within about 3 minutes. Showing that it cannot form, like the evolutionist says, over millions and millions of years of cooling down. It had to have formed literally within almost, like I said, within a 3-minute span of time. Now, going on, it says the half-life of a radioactive isotope is the time required for the half of the atoms in any collection to decay. If 1,000 atoms exist in a certain time, then only 500 will remain after the one half-life. After 2 half-lives, only 250 atoms. And so, now if you guys will remember the carbon-14, I showed you the what we would consider a container of water, and then the half-life would be half of that, and then half of that would another time span. The carbon-14 has a different half-lives than this right here. But if you'll remember that half-life, the vocabulary of the half-life, you can see that. So some of you that haven't seen it, just go back to my carbon-14 and you'll see what I'm talking about. But it says, let's see, going back, it says after 2 half-lives, it would have 250 atoms left of the original collection would remain, and so forth. Half-life and decay rates are closely related quantities. Isotopes that decay quickly have short half-lives. Those that decay more slowly have longer half-lives. At present, and this is information from 1986, uranium-238 is thought to is decaying at a very slow, with a half-life of 4.5 billion years. And again, that's information from 1986, and so I don't know if they've got any other change other than that. Now, this chart here with the uranium-238, all the other abbreviations there, I put it on the right hand and the left side if you guys want to pause the screen and look at that. And so, but this right here is the chain reaction decay of uranium-238 to lead-206. Now, what I did is I made another chart up myself. It's basically the same thing, the same decay from U-238 all the way to, or uranium-238 to lead-206, but I just made this one up so I could add some stuff to it. But you have these things called alpha particles and beta particles. Now, the alpha particles are those little A's there. If you'll notice, uranium-238, and right between that one and the next one, you've got that A. That means alpha. That means alpha. Now, the B is beta. Now, the alpha particles are ejected at each decay step and have different energies. Now, the energies, you'll see it on the next chart that I'm about to show. They have an abbreviation of that, of an MeV, which means million electron volts, producing 8 different rings within different distances in a uranium halo. Now, from what I understand, the beta particles, they don't interact because of the material and what's being ejected out. They don't have, you can't see them in the mica. They don't interact with mica the way alpha particles do. So you're not going to see the rings of beta particles like you would on the alpha particles. And so, but while uranium-238 has an extremely long life, which is 4.51 billion years, some of the intermediate steps proceed quickly. Polonium isotopes are unstable and decay rates can be days to microseconds. A polonium sphere would not take long to form, only under 302 degrees Fahrenheit. They would be able to form. But a granite melt would require time to cool and harden. Granite would not record a halo until it has hardened. A fast decaying isotope and a slow forming rock, you're not going to get it. That granite, from the time it started its melt to the time it hardened, it has to be fast, guys, because those polonium halos would dissipate into nothing. And so by though that granite would have to form fast, and from what the measurements that they've given, under 3 minutes, way faster than what the evolutionary model is showing. Now, if you'll notice underneath that information there, I've got 3 lines there: polonium-218, polonium-214, and polonium-210. Now, the polonium-218 has a half-life of 3.1 minutes. That's it, 3.1 minutes. If it hasn't cooled before then, it's going to dissipate and you will not see it. Polonium-214 has a half-life of only, get this guys, 164 microseconds. 164 microseconds. Listen, that's a blink. and polonium 210, which has a half-life of only 138 days. And so now, guys, I'm going to have to stop right there because I'm looking at about 20 minutes. And I can't believe I'm 20 minutes into this. But we're going to come back to this and we're going to keep on going. And so, but kind of chew over what I've stated. I am going to put some links in the description below for my YouTubers and Rumble. And my Facebook people, I'm going to put some links up above. And so you guys can still get into this material and watch it. And again, if you want to get the book, Creation's Tiny Mystery by Dr. Robert Gentry. This is a very good book. But guys, we're going to continue on with this exciting thing. I got to stop now, but it's going to be wild. It's going to be wild, we'll say the least. And so, but you guys take care. I love you and hope the Lord blesses you real good. Bye-bye.